session on using calculus turning points to calculate what the maximum voltage would be if we added together these two signals. If you can call 25 and 30 volts signals, probably you could say that they're millivolts. Anyway, so we're going to add these two together and we're going to use turning points to calculate what our maximum voltage is. Bear in mind the maximum voltage will be at a maxima when it turns, where the turning point is. So you've got a maximum and a minimum, we're looking for the maxima. Now in this example, to start with anyway, we're going to make an assumption that it occurs here and not that our 0 point's somewhere over here and it occurs as a second maximum displacement, shall we say. Also, you could solve this by using things like trigonometry identities, but we're not going to do that in this example. That would probably be as easy a way to do it with something like this formula. It's quite easy to add these two together, a sine and a cosine with the same frequency. It's a very simple formula. But if these were something like different frequencies, or the frequencies shown here in the 100 pi, which is the angular frequency, if they're different frequencies, it won't be as easy to do it with a trig identity. Anyway, we're going to do it with turning points anyway, because that's the whole point of the exercise. Okay, and the thing to remember as well is make sure your calculator is in radians. So I'm going to stick that up there as a reminder. So that's an important thing, make sure your calculator or whatever you're doing the calculations in is working in radians. If you're using Excel or Wolfram Alpha, for example, it will actually do it by default in radians. Excuse me. Okay, so let's, with no more messing about, let's get on with it. So it's straightforward. So when you're looking for the turning point, so I've rubbed it out, but when it's a turning point is when the gradient is 0, so in this case it'd be dE over dt would equal 0. So the only way to do that, well, one of the ways to do that is to differentiate this, set it equal to 0 where the gradient is 0 and see what we get. So let's have a go. So it's fairly straightforward. So dE over dt would be, so the differentiation of that and the differentiation of that, so what's inside the bracket comes out and multiplies into the figured out fronts, so that would be 25 times 100, so 2,500. The pi comes out as well, and then it's cosine, no minus sign needed for this. The stuff inside the bracket stays the same, remember that. This is now minus, because it's going to be minus sine. The 100 is going to come out and multiply that, so I'll get 2 zeros to make it 3,000. Pi comes out, sine, and the stuff inside stays the same. Okay, so that's it differentiated, nice and easy. Next step, set it equal to 0. So when all this equals 0, this part obviously must equal that part, otherwise it won't equal 0. Add them together or subtract them, adding them because one's a negative. It's going to equal 0. So in other words, that must equal that. And it would have been easier just to change that to equals in the middle. But for sake of completion, I'll do all the steps. So I need to sort that in a way that I can find out what value of t that equals that. So we've got to get the t's on their own basically. We've got to get at outside of everything. So the step here is to bring this from this side to this side. So I will get this. So divide through, in other words. will equal, and then I'm going to divide through by cosine, so that'll bring that cosine to be over here, so as a divide. So I'll have sine 100 pi t divided by cosine 100, pen's running out. Not to panic, I do have another one. Pi t, and one of the trig identities is tan of x, tan of theta is equal to sine divided by cosine, if you've got the same value inside the brackets. So that would be equal to 100 pi t. So that part there is a trig identity, this bit here. So in other words, that equals that. Now this will cancel, so leave me 25 over 30. So I'm almost back where I started on that regards here. Okay, so to find what t is, I need to get this from outside the function, from inside the function, bring it out. So I'll do the inverse of the tan. Inverse of tan gets rid of the tan function, but I have to do it to the left hand side as well to keep everything balanced. So I now have the inverse of tan of 25 over 30. Okay, equals, so that tan's gone, so it equals 100 pi t. So if I divide through by 100 pi, I will have t equals this divided by 100 pi. Will I not? Let's put that up here. Therefore, t equals inverse of tan minus 1 of 25 over 30 divided by 100 pi. That gives me an answer of, I see my notes, somewhere on here, 2.2114 times 10 to the minus 3, or 2.2114 milliseconds. Okay, let's write that down. So 2.2114, what I said now, 114 times 10 to the minus 3, which is milliseconds, of course. Okay? So that is telling me that this here, that time is when my waveform is there. Or is it? Maybe it's there, maybe it's a minima. So we have to test it to see if it's a minima or a maxima. So that's the part 2 that we're going to do. If it's not, then we've got to do a few other steps which I'll cover at the end of the video. Okay, let me make a note of that value. 2.2114 times 10 to the minus 3. Okay, so how do we find if it's a maximum or a minima? Well, there's 2 ways of doing it. This formula here tells us what the gradient is. So what I could do is I could change the time and slightly go to the left and see if I get a positive answer, like that, and if I move to the right slightly, so say do 2 milliseconds for example, and that would, if I get a positive, that would indicate that it's going uphill, and if I get a negative by going to the right, so say 2.5 for example, that would tell me it's a maxima. Obviously I'd get the opposite effect for the minima. Okay, so that's a test. And the other way, of course, that you're probably all aware of is to differentiate again. So if I differentiate this again and then put my value of this into the formula and see if I get a positive value or a negative value. So I'm going to rub this lot off to make space for myself. Okay, hope you're with me so far. So double differentiation. So this is the usual way we do it because it's maybe slightly quicker than the moving to the left and moving to the right, and maybe not. whichever way you want, you do. So I'll just re-clarify that. If that should be d2e dt squared, double differentiation. If I was looking at this approach, see if we've got a positive there and a negative there, that's my value of t when it's there. So I would go to the left value on here, left that way, and put a smaller number in. You don't have to go mad. In fact, it's best not to go mad. That turning point only happens at a very minute, a precise time actually. So we'd move to the left, put 2 in. So we'd put 0.2 milliseconds, I mean by that. So I'd put that into there, and into there, and see if I get a positive, and then I'd put a number to the right and put a 2.5 and see if I get a negative. So that's one approach you can do. There's nothing wrong with that way at all. It's quite informative. It works, in other words. This is the other method. So I differentiate this again. So this is going to be, so that 100 pi t is going to come out again and multiply in. So I'll have 2, 5, 0, 0, 2 noughts added, pi squared. Okay, sine, differentiation of that, the stuff inside the brackets stays the same, and I can almost hear you all shouting, saying don't forget the negative, it's a minus. Cosine becomes a negative sign if it starts as a positive, and this stays the same, which is already a negative. So this is 3,002 zeros added on with that 100 squared, and then pi squared, and then the cosine this time, 100 pi t. So that's it differentiated twice. And then what we do is we take that value there, we put it into here to see what we get, to see what the answer is. And the answer is, if you do that, we get this. Again, I'm referring to my notes. We get a negative 0.0 3 zeros 9 39 actually. It really does not matter actually that I made that mistake in the slightest, and it goes on, and it doesn't matter because this is the only thing we cared about, that minus sign there. If it's a minus, it's a maxima, so that means it's that way. If it's a positive, so this is a minus, if it's a positive, it's a minima, it's that way. Okay, so that tells me it's a maxima. Straightforward. Now I'm going to show you in a bit what to do if we've got a minima, because the question at the beginning was that I didn't actually word it, put it into words, but if I look at my sheet, the words are: find the time that the first occurrence of a maximum voltage is achieved. Okay, so obviously waves like that, and we want to know when we get the first value of it. So if our 0 was there, the first one would be here, so we'd actually get a minima. Okay, so it occurs there. Fortunately, our 0 points gives us it there. It's come out straight away. Okay, so let's see two things. Firstly, what value is it at that turning point? What's the maximum voltage? We know we've got 25 and 30 added together. Let's assume they're volts. 25 and 30 added together, obviously you don't just add them because they're out of phase with one another. We suspect it will be greater than the biggest, so bigger than 30, so that's a bit of a guide. Obviously it can be smaller, depending on the phases. You can actually, if there were, well, because of different volts, not in this case, but if you have 2 volts the same, two signals, and they've got 180% out of phase, they actually cancel out. So you get a 0 resultant waveform, which is how noise cancelling headphones work. But that aside, let's see what we get. We know it's going to be somewhere anyway between 0 and less than adding them two together. let's have a look. So what you would have to do is go back to my original formula, put this value in to there, where t is, to the two t values, and do the maths. And the answer to that is simply when you use a calculator or Wolfram Alpha or something, we've got 39 volts. 39.033 volts, which is very reasonable. Seems very reasonable, there's nothing wrong with that. Okay? So that's that bit done. So that might be a question you might be asked. The next part of the puzzle is what would happen, what would you do if it was a minima? So going back to this, we got a minima when we did the double differentiation. Instead of a minus number, we've got a positive number, it's a minima. So then we'd have to, what we've got then is this situation. We've got something like this. So that was the value we've got. Part of the reason for this is when you use the inverse of tan function in your calculator, or the inverse of sine or cosine, let's take a sine wave. Okay, sine wave starts there. You've got infinite, say you get an answer that's 0.5, sine 30 is 0.5. Okay, there for example. 30 degrees. Okay, if you're in degrees. It also occurs there. It also occurs there, and it occurs forever. It's infinite, it just keeps happening. And it also happens on the negative side, as your minus angles, or minus time if you're in time, which in radians we are in time. Your calculator obviously can't give you infinite answers. It can't even give you, it won't even want to give you more than one answer, because one answer is enough. So what it does is it gives you, going back to this, it gives you the answers from here to here. So it gives you that range there of answers. Okay, so that's why you can get negative answers. Well, obviously you can get negative answers anyway, but it's why you tend to be half of them are negative and half of them may be positive. So it uses that. If it's a cosine wave, which is, draw it like that, you're going to get, they're both going to be positive. Okay. He says thinking about it. Yeah, it would be, it'd have to be. And then tan's another thing as well. It can only give you the values from here to here. Tan's a bit weird because obviously it's got asymptote answers, but anyway. So it's only giving you this range here, so it's going to give you that one there. So that's why you'd get a negative answer, or it could be on the other side of the curve, you don't know. So you'd have to then do a bit more research, and the best way to do it is, it's going to be that one. So all you've got to do is add this to your value of time. And what is that time? Well, this is a full period. With a t. So obviously that's half a cycle, a full cycle is a period, a full period. So it's going to be t divided by 2. So that's what you would have to do. And how would we do that? Well, we'd look at the frequency, and we'd have to do a bit of rubbing off here. How do we find what the period is? We use the angular frequency. This is angular frequency, remember. We need to find out what the frequency is. So frequency is found from, let's start at the beginning. Omega angular frequency, which is what this is equal to 2 pi f, and we want f. So therefore, let's have a therefore f is equal to omega divided by 2 pi, it's just that rearranged, 2 pi, and our omega is 100 pi, from there, divided by 2 pi, so the pi's cancel, so that is actually 50 hertz, which is what the mains is in the UK and most of the world actually. So that's my frequency, and how do we find the period from the frequency? Well, it's quite simple, it's just the period is equal to 1 over f, the frequency, which is 1 over 50, which is 0.02, half of that, because we want half, not a full period, so 0.0, get messy here, divided by 2 equals 0.01. So what you would do is add 0.01 to the answer we got previously, to this value actually. So we'd add that. It's the beauty of radians, by the way. You automatically, it fits in with time automatically. So that's, we were in frequency, but it's actually giving it in time. So we add that as a time to that. Remember that that's actually 0.00221. So you'd end up with that added to it. Okay, and that would give you the maxima point, the first occurrence of a max voltage, rather than the maximum displacement in the minimum voltage, if you see the difference. Okay, so that would be the final step you need to do then. Not massively, but it's obviously made the whole process that little bit harder. But if probably be worthy of a distinction question, that. Okay, thank you.